Let's take another example. This example says consider turbine. So in this turbine we have inlet steam at 3 megapascal at 823 Kelvin, and we have exit steam at 0.1 megapascal and temperature 473.15 Kelvin. So we have the pressure and temperature of the inlet, pressure, temperature of the outlet. You can find anything that you need. You can find internal energy, you can find enthalpy, you can find entropy, anything for the inlet and outlet now you can find, because you have two information given for each stream. The first requirement, how much entropy is generated for each kilogram of steam. So here we have mass is 1 kilogram. So the mass is kilogram time independent, so we'll use the time independent form of the entropy balance. If the mass is 1 kilogram per hour, for example, so this is mass rate, so we'll use the rate form of the entropy balance. 1 kilogram of steam that goes through this turbine. Then we have the second requirement, what is the maximum work can be obtained for the same amount if we have the inlet steam and the outlet pressure 0.1 megapascal. So let's start with the first requirement here we have. So in this requirement, so it's required to find the entropy generated. The only equation that has this term is the entropy balance. So we will start with the entropy balance. So the entropy balance so we have accumulation. This is inlet minus outlet plus Q over T plus generated entropy. So in this example, the process is a steady state, so the accumulation will be 0. The process is adiabatic, so this term will be 0. So always this term is cancelled if you have steady state process. This term will be cancelled if you have adiabatic process. So what we will have at the end, so at the end we can say the S generation, this one will be the outlet entropy minus inlet entropy, which is mass times outlet specific entropy minus inlet specific entropy. Mass is constant, this is conservation of mass, so inlet mass is the same as out mass. This is why I take mass as the common factor. So what we need to find here in this example, we need to find the generation per kilogram, so we need to define the divide by mass, so the generated entropy per mass. This is the term that we need to calculate. In the problem, he said I need to calculate the generated entropy per unit mass. So this one will be the outlets specific entropy for the outlets minus specific entropy for the inlet. And how I can find entropy for the inlet and outlet, this will be steam tables. Again, and I have all information given. So I have for the inlet, I have steam. This steam at 3 megapascal and 8 to 3.15 Kelvin. You can use the Excel file to put these numbers, and then you can see that the specific entropy of the inlet, this one will be 7.3768 kilojoule per kilogram Kelvin. And the same thing, you can go to the outlets. So the outlet we have steam at 0.1 megapascal and the temperature was 473.15 Kelvin. So I have two information. Then directly you can use the appendix. Then from the appendix you can find the specific entropy for the outlet. This one will be 7.8356 kilojoule per kilogram Kelvin. So I have all the information now given. So substitute in the entropy balance equation. Then we can say the generated entropy per unit mass. This one will be 0.45 88 kilojoule per kilogram Kelvin, and this is the first requirement we have. Clear? Any questions? Okay.
How do we get temperature?
It's given. So the temperature, pressure of the inlet, temperature, pressure of the outlet. Questions? Second requirement says we need to calculate the maximum work that can be obtained from this turbine. Okay. So what can you understand from this one? So you see this statement, maximum work. So in order to obtain the maximum work from any process, so here he is trying to telling you that you need to make an assumption. Do you need to assume the process is reversible or irreversible? Should be reversible. So again, this word here, this maximum work, is just giving you this information to make you do this assumption. You need to assume the process is reversible process, because only reversible process will give you the maximum work. Okay, so here in this one, the second requirement, we need to find the maximum work. And in order to find the maximum work, then we need to assume the process is reversible. This is the only type that can give you maximum work. And also it's given that the process is adiabatic. So now you have your process is reversible. This is your assumption, because I need to calculate the maximum work. And originally the process is adiabatic. So reversible adiabatic, this is equivalent to isentropic. And this means that we have the entropy for the inlet and outlet will be the same, because we have generated entropy, this will be 0. So all of this, like new information, just you need to understand from the statement, from the requirement. We need to calculate the maximum work. So the maximum work only can be calculated if the process is reversible. Then he's telling you assume the process is reversible. And he's telling you in the given the process is adiabatic. So reversible adiabatic means isentropic. Based on this word, then you can know that inlet entropy, outlet entropy will be the same. There is no generation of entropy in this requirement. Okay? So in order to do this one here, this is what we will start with. The work, this is obtained from the first law of thermodynamics. So let's recall the first law of thermodynamics. So if you done with this one, then you will have, let's do it step by step. Let's recall chapter 3. Let's do it one by one. This is the general form of the first law of thermodynamics for open system, which is the case we have here. So we have the accumulation is enthalpy, velocity, GH for the inlets minus enthalpy, kinetic potential energy for the outlet, work of expansion, contraction, shaft work plus Q. Okay. The process is a steady state, so the accumulation term will be 0. Here we have turbine. He didn't mention any changes of the diameter or cross section of the inlet and outlet, so we can assume inlet and outlet have the same kinetic energy. So V square over 2, this term will be cancelled with the inlet and outlet. There is no change in the elevation, so GH term will be cancelled. There is no expansion or contraction, so this term will be cancelled. The process is adiabatic, Q will be cancelled. So what is remaining? Enthalpy of the inlet, enthalpy of the outlet, shaft work. And this is what you need to find, shaft work, because in turbine you have rotating equipment. Okay. So if we get back to this one, so from this first law of thermodynamics, this will be the equation we have. Shaft work divided by mass flow rate, this will equal enthalpy of the outlet minus enthalpy of the inlet. And this is the term that you need to calculate. This is what we need to find. Okay. So let's find the enthalpies values for we have. So for the inlet, I have steam at 3 megapascal and temperature is given, which is 8 to 3.15 Kelvin. Then from the appendix you can find specific enthalpy for the inlet. That will be 3569.7 kilojoule per kilogram. And also we need to find specific entropy for the inlet. That will be 7.3768 kilojoule per kilogram Kelvin. Now I have the inlet enthalpy. Now I can go to the outlets. What I know for the outlet is that I have steam at 0.1 megapascal. But now the temperature is not the same as the first requirement, because now we have different process. We have reversible process. But we know that for the outlet, I know the specific entropy for the outlet, because it will be the same as specific entropy for the inlet, because we have isentropic process. So this is 7.3768 kilojoule per kilogram Kelvin. So I have two information, and this is all what I need to use the steam tables. So now you can use the steam tables for this one in order to find the outlet temperature. This one will be 103.1 degrees Celsius. See, the temperature change only because you assume the process is reversible. And the outlet enthalpy, this one will be 2682.3 kilojoule per kilogram. Now we can substitute the first law of thermodynamics, and we can find that the maximum shaft work we can obtain from this process, this one will be negative 887.4 kilojoule per kilogram, and this is the requirement. This is the maximum work that can be done, and this work done by the system or on the system. Done by the system. Here we have negative sign, so this negative sign over here means we have work done by the system. So we have fluid. This fluid is rotating the blades of the turbine in order to give you the work that you need.